All right, now we're going to talk about the type of reaction called an oxidation reduction reaction, also known as a redox reaction. And in these types of reactions, it is electrons that end up getting transferred. So electrons are transferred. In an acid-base reaction, it is protons that end up getting transferred from the acid to the base. In a redox reaction, it is a substance that is oxidized that transfers an electron to something that's reduced. Let's define these two terms first, oxidation and reduction. In oxidation, this is a process in which a chemical entity loses an electron. And the reduction is the opposite. In a reduction, that's a process in which a chemical species gains an electron. Gain of an electron. And this may sound a little odd, that when you gain something, you're reduced. But we have to remember that electrons are negative. Kind of like debt. Debt's a negative thing. So if you gain debt, the amount of money you have is reduced. And you want to think about oxidation and reduction in the same way. If something gains an electron, it's gaining something that's negative, and so that entity that gains the electron is reduced. There are some mnemonics that are used to remember this. And one of them that I like to remember is Leo the lion says grr. And from this mnemonic we can see if you lose an electron, you're oxidized. If you gain an electron, you are reduced. And we'll need to remember that oxidation and reduction go hand in hand. When something loses an electron, it's not lost from the universe. There's a law of conservation of mass. There's a law of conservation of charge. So if something loses an electron, that electron has to go somewhere. So if something is oxidized, it's lost an electron, something else better gain that electron. So something else is going to be reduced. And if something's being reduced, if something's gaining an electron, that electron just doesn't pop into existence from nothing. That electron has to come from somewhere. So if something is reduced, something else must be oxidized. If something's oxidized, something else must be being reduced. If you're a little concerned about the vocabulary, don't worry, it's going to get a little worse. So there's some other terms that are used when we're dealing with oxidation and reduction. And those two terms are oxidizing agent and reducing agent. And what these terms mean, what they refer to, is a chemical that does something. So an oxidizing agent is a chemical that oxidizes other chemicals. So that means if it's an oxidizing agent, it causes other things to be oxidized. So we're going to remember this. If something's oxidized, it loses an electron or multiple electrons. So if something is oxidized, it's losing electrons. If something's an oxidizing agent, it's causing something else to be oxidized. So it's pulling electrons from something else. It's kind of like an electron sucker. So the oxidizing agent gains electrons from something else, so the oxidizing agent is reduced. If I'm making sense to you, great, you're tracking. If not, you might want to review the video here and go back and look over the definitions again. In a similar way, we're going to think about a reducing agent. A reducing agent is a chemical that causes something else to be reduced. So a reducing agent is going to cause something to gain electrons. In a sense, a reducing agent is like an electron gun, so to speak. It shoots electrons into something else. it causes something else to be reduced. And so the reducing agent gives up electrons, and so the reducing agent is oxidized. Once again, if you're tracking this discussion, good. Keep moving forward. If not, maybe pause and go back through the definitions again. When I talk about oxidation and reduction, I tend to focus on something in chemicals that are called oxidation numbers. And so what we'll do with looking at oxidation numbers, that'll help us to determine whether something's being oxidized or reduced. So we're going to spend quite a bit of time going over oxidation numbers. And there's going to be some rules that we're going to apply that'll help us understand whether something's being oxidized or reduced. So first, let me just tell you how we're going to look at this. If something's has its oxidation number, I'm going to abbreviate oxidation number like that. If something has its oxidation number go down, I hope it makes sense to you that we would say that that something is reduced. So if something has its oxidation number goes down, it is said to be reduced. And the opposite is true. If something has its oxidation number go up, then we say that that entity has been oxidized. So if something has its oxidation go up, it is said to be oxidized. And so we're going to need to spend a little bit of time looking at different chemical species and determining whether those chemical species are having their oxidation numbers go up or their oxidation numbers go down. So obviously it's important to understand how to find what the oxidation numbers are of different entities in different chemical species. So I am now on slide, looks like 21 of PowerPoint 3A types of reactions. I'm gonna write down the rules for determining the oxidation numbers of an element in some sort of chemical. And they look like this. Rule 1, the oxidation numbers of elements in something must add up to the charge. And by the way, these rules that I'm writing here, they're not rules that we're all going to follow. The rules are listed in order of importance, and so this rule that I'm writing here first is the most important rule. It must be followed. You violate this rule, you're going to go off the rails. It's going to be wrong. As we get lower and lower on the list of rules, they're going to go from rules to suggestions. So it's not like these are the 10 commandments. It's more like the one commandment and then a bunch of suggestions that get less and less important as you go down. So keep that in mind. So let's look at this particular rule here. Let's say I'm looking at the sulfate ion, and we're going to, we're not going to go through the whole thing yet, but we're going to sort of apply rule 1 to this. When I look at sulfate, I see 1 sulfur, and I see 4 oxygens. And what I'll be doing is I will be assigning oxidation numbers to the sulfur and the oxygens, and then all the oxygens are going to get the same oxidation number because I can't tell the difference between these oxygens. They're all identical. And so I'll assign an oxidation number here. I'll assign the same oxidation number for all 4 of these. And when I'm done, if I add up all these numbers, they had better equal, you guessed it, -2. That's what the rule is telling me. I'm going to add up all those oxidation numbers, and it had better equal the charge when I'm done, or I'm in trouble. All right, so that's rule number 1. We'll worry about the rest of all this later. Let's go to rule number 2. If you have a pure element, the oxidation numbers of the atoms in a pure element get the oxidation number of 0. So you got a pure element. Oxidation numbers are going to be 0. So for example, if I have sodium metal, I'm going to give the oxidation number of the sodium in sodium metal. It's just an element. I'm going to give it a 0. But be careful. You might see this. I might see sodium ion. Now, first of all, sodium ion is not going to be an element. This ion is always going to be paired with an anion. So it's going to be like locked in sodium chloride, which tells me this isn't an element. But if you make a mistake and you think it's an element, and you try to say, well, I'm going to go ahead and give this an oxidation number of 0, rule number 1 should be shouting at you. If I try to give this an oxidation number of 0, hey, that's not equal to the charge, is it? And so there would be a caution there that tells me, you know what, I should probably assign sodium in the sodium ion an oxidation number of +1, because this is the most important rule. All right, let's go to rule number 3. Rule number 3 is assign oxidation numbers of monoatomic ions, basically their charge. So what's a monoatomic ion? Let me draw 2 ions down here, sulfate and sulfide. Only one of these is a monoatomic ion. Remember, this is a polyatomic ion. It's made of more than one element. This rule doesn't even apply to this substance because it's not monoatomic, so I'm not even going to consider this. But this rule would apply to the sulfide ion. It is a monoatomic ion. It's an ion that comes from a single atom. And so this one's pretty easy. I mean, its charge is -2. And rule 3 tells me, give it a charge of -2. And if I do that, the -2 that I assign to this is going to equal the charge on the ion. And so rule 1's intact. All right. Rules 4 through 7 are suggestions that you give particular elements in substances. So rule 4 says assign fluorine an oxidation number of -1. Rule 5 says give hydrogen atoms an oxidation number of +1. Rule 6 says give oxygen an oxidation number of -2. And finally, rule 7 says give all the other halogens, remember fluorine's a halogen, rule 7 says give all the other halogens an oxidation number of -1. Please remember that this rule is just a minor suggestion. We're not always going to use this. We're not always even going to assign oxygen an oxidation number of -2. You're more likely to assign hydrogen an oxidation number of +1 than you are to give oxygen an oxidation number of -2, and so on. As you move up the chart from the rules from rule 7 to rule 1, the rules get more and more and more important. Okay. Probably a good idea for you to leave slide number 21 open as I go through some of these examples. We're ready to apply these rules. Let's do this. I'm going to take 3 different substances. I'm going to take elemental oxygen gas, the stuff we find in the air. We'll take water, H2O, and also let's take hydrogen peroxide. We'll make that a liquid. Yep. And what we're going to do is we're going to assign oxidation numbers for all of the elements in each of these 3 substances. And hopefully by doing so, we'll gain some insight into these rules. Now, fortunately, all of these are neutral compounds. And so when we're done assigning oxidation numbers for all the elements in oxygen, for example, we add them up, it better equal 0. This is rule 1. Same thing for water. Same thing for hydrogen peroxide. We'll do sulfate. We'll do sulfate as well. We'll do that one last. Let's save that one. Okay, let's do this for our oxygen. I have two oxygen atoms, and when I add up the oxidation numbers for this oxygen atom and this oxygen atom, it had better equal 0. This represents a 0 here. These represent oxygen atoms. So now I'm going to go to rule 2, which actually applies here. This is a pure element. And it tells me to assign the oxidation numbers of atoms in a pure element 0, and this works beautifully. It works perfectly, because 0 plus 0 is 0. So I'd assign the oxidation number for both oxygen atoms in the oxygen molecule an oxidation number of 0. That one's pretty simple. Let's go here to water. I need to assign oxidation numbers to both hydrogen atoms. There's two of them, and they're identical, so these are going to get the same oxidation number. Whatever I assign to this one, I'm going to assign to this one. We're also going to assign an oxidation number to the single oxygen, and when I'm done, it better equal 0, because there's no charge on this thing. Starting to go through the rules. I've already, when I write this out, this means Dr. K is making sure that rule number 1 is followed. I go to rule 2, it doesn't apply. This is not a pure element. I go to rule 3. Rule 3 doesn't apply. This is not a monoatomic ion. I go to rule 4. Rule 4 doesn't apply. There's no fluorine. But when I get to rule 5, the suggestion there is to give your hydrogens a +1. Now at this point I'm locked in. I have to assign a number to the oxygen that when I take this one and add this one and then do whatever I do here, I better get 0. It's pretty easy to see. We better assign oxygen an oxidation number of -2, or we're going to go off the rails and violate rule number 1, which is the last thing we want to do. So I'd write up here +1 for the oxidation number of hydrogen and -2 for the oxidation number for oxygen. And I just want to pause here for a second and make sure you understand that these are not charges. You know, water is neutral. These do not represent full-blown charges. They are an accounting system to try to help us understand where electrons are going to and coming from in redox reactions. So keep that in mind. Oxidation numbers are different than charge. Oxidation numbers help us understand what's going on in redox reactions. All right, now let's do the same thing for hydrogen peroxide. Well, it looks like I've got 2 hydrogens and 2 oxygens. So I'm going to take a hydrogen and another hydrogen. I'll assign the same oxidation number for both of these because they're chemically identical. And I'm going to take 2 oxygens. And once again, I'm going to assign the same oxidation number to both of these oxygens because they're identical in the molecule. And when I add all of this up, it's got to equal 0. So once again, we'll go through the rules. Rule 1 obviously applies. That's me writing this here. Rule 2 doesn't apply. This is not an element. Rule 3 does not apply. It's not a monoatomic ion. Rule 4 doesn't apply. It has no fluorine. But Rule 5 does apply. There's some hydrogen atoms. I give this a +1. I give this a +1. And now I'm locked in because I have to assign the same oxidation number to both of these oxygens because they're identical. Well, I hope you see pretty easily here that if I give both of these a -1, +1, +1, -1, -1, that gives me 0. And so my oxidation number for the hydrogen is going to be a +1 for both of them and -1 for both oxygens. And I have now assigned the oxidation numbers for all of the atoms in all 3 of these compounds. And now we're ready to see a little bit of how something might be oxidized or reduced in a chemical reaction. For example, let's say there's a chemical reaction where oxygen gets converted into water. When oxygen gets converted into water, notice that the oxidation number of the oxygen goes from 0 to -2. That's a drop in oxidation number. That's a reduction. So we can say, in a particular chemical reaction, that oxygen gets reduced into water. And that actually happens in a chemical reaction that you're probably familiar with. I'll write it here on the board. Recognize that thing? You biologists should recognize it. This is respiration. And in this reaction, hey, look at this. Oxygen gas gets reduced to water in the process of respiration. And that's an appropriate thing to say in this particular reaction. We can also look at this in reverse. We can think of a reaction where water gets converted into oxygen. Where might that happen? Well, that happens in this reaction in the reverse direction. Where does that happen? Okay, that doesn't happen on its own. 6 carbon dioxides and 6 waters going to sugar and oxygen. You know where that happens? That happens in plants. Photosynthesis. We ought to put some energy in here, you know, sunlight. That better go in here or this reaction won't happen on its own. But nevertheless, water in photosynthesis gets converted to oxygen. And if we look at the oxidation numbers, we're able to describe what's going on in terms of a redox reaction. In photosynthesis, water, where oxygen's a -2 oxidation number, gets converted into oxygen, where the oxidation number is 0, the oxidation number is going up, and so we say water gets oxidized in photosynthesis. And once I've recognized this pair, where this is the, what did I say, that's the oxidation, isn't it? Well, the other pair must be the reduction. This is where, you know, if this is, what's that doing? That's losing electrons. If this is losing electrons, it must be that the carbon dioxide is gaining electrons, and we would say carbon dioxide is getting reduced into glucose. And you can actually go back and you can end up assigning the oxidation number for carbon in carbon dioxide and the oxidation number for carbon in glucose. And in that case, you had better see the oxidation number of the carbon going down. Hope I said that right. Let me just check. Yep. This is going up, so that's an oxidation. In this case, it's going down. That should be a reduction. Let me just check it. Let's just make sure we see it. Okay. Let's see, 6. Oh, I don't want to worry about that, do I? So I want to assign an oxidation number for the carbon and the 2 oxygens and carbon dioxide. When I'm done with that, better be 0 because this is neutral. Rule 2 doesn't apply, it's not an element. Rule 3, it's not an ion, so we're not going to worry about that. There's no fluorine there. There's no hydrogen here. We actually get all the way down to rule number 6 here, where we're going to assign the oxygens a -2. Now we're locked in. The carbon's got to be a +4, correct? So that means our carbon's a +4. And I'll just write this in here so I know what's going on here. A -2 and a 0. And now let's do the same thing for glucose. Let's see what that oxidation number is and the carbon in glucose. It better be less than 4, +4. I did something wrong. I'm telling you something wrong. Oh boy, there's going to be a lot of these. I'm not going to draw out all the lines for this, okay? Because it's going to be too many lines for 6 oxygens, 12 hydrogens, and 6 carbons. Hopefully I can just draw 6 carbons here. And we're going to add to that whatever I assign to our 12 hydrogens. And I'll assign something to my 6 oxygens. And when I add all those up together, it had better equal 0, because there's no charge on glucose. If I go through the rules, rules 2, 3, and 4 don't apply. But when I get to rules 5 and 6, they do. It says give a +1 to your hydrogens. Notice there's 12 of them, so that's a total of +12. When I get down to, this is an oxygen, not a 0. So when I get to oxygen, it says give an oxidation number of -2 to all the oxygens. -2 times 6, that's going to give me a -12. Those cancel. What am I going to give my 6 carbons? I don't want to give them anything, right? 6 times 0 is 0. 0 plus 12 minus 12 is 0. So there we have it. The oxidation number on the carbon goes from a plus 4 down to a 0, and we see in photosynthesis, carbon dioxide gets reduced into sugar. We also see that water gets oxidized into oxygen. In respiration, it's the opposite. Respiration, it's going in this direction. We would say in respiration that glucose gets oxidized to carbon dioxide, and we would say that oxygen gets reduced to water. We already said that before. But you'll notice here, this demonstrates how these oxidation and reduction reactions, they go hand in hand. If something's being oxidized, something else must be being reduced. If something's being reduced, something else must be oxidized. All right. Let's think about this. Let's say there's a chemical reaction where water gets converted into hydrogen peroxide. Is that an oxidation or a reduction? If a negative 2 goes to a negative 1, notice the oxidation number is going up because a negative 2 is lower than a negative 1. So we would say that hydrogen peroxide, oh, I got it the wrong way, water would get oxidized into hydrogen peroxide. Okay. Why don't you go ahead and try to assign the oxidation numbers to all the elements in sulfate. Give that a shot, pause the video, and we'll come back and check it out. All right, let's give this a shot, see how we're going to do this. I'm going to assign an oxidation number to sulfur and 4 oxygens, and when I'm done, I hope you remembered this. This is the first time that you've done this on your own where we're going to need to make that charge equal to a negative 2. It's not neutral. As we go through the list of rules or suggestions, of course this is a rule. Rule 2 doesn't apply, this is not an element. Rule 3 doesn't apply, it's not a monoatomic ion, it's actually a polyatomic ion. So we don't pay attention to rule 3. There's no fluorine, so we don't deal with rule number 4. Rule 5 is hydrogen, no hydrogen. We get to rule 6, and finally we see, okay, I'm going to give negative 2s. Wait, that looks terrible. Negative 2, negative 2, negative 2 to all of my oxygens. So negative 2, negative 4, negative 6, negative 8. What do I need to add to negative 8 to give me a negative 2? A positive 6. So the oxidation number of sulfur is plus 6 in sulfate, and the oxidation number of oxygen in sulfate is going to be a minus 2. If you look at slide number 22, there are some opportunities for you to determine the oxidation number of various compounds. I'd suggest you take some time to go over that. At this point, I want to move to slide number 23, and we want to look at slide number 23 and try to determine what's oxidized, what's reduced, and also what's the oxidizing agent and what's the reducing agent. Why don't you pause the video and try doing this for the 4 reactions that you see on slide number 23, and then we'll come back and do a couple of them together. All right, these are the 2 reactions that I have chosen to sort of demonstrate the answers to this problem. What's oxidized, what's reduced, what's the oxidizing agent, and what's the reducing agent in each of these 2 particular reactions. We'll look at the first one, because we already assigned the oxidation numbers for all of these particular compounds earlier, and you might remember that it was a 0 here for oxygen atoms in the oxygen molecule. It's a minus 2 for the oxygen atom in water, and it's a minus 1 for the oxygen atom in peroxide. And in this case, it's tricky. This is a really tricky one. You have to recognize that there are 2 hydrogen peroxide molecules here. So I'm going to draw it like this, so we can see what's going on a little better. So the way to envision this is we say, okay, this hydrogen peroxide molecule, we'll say this one gets turned into some water. And if that happens, I see that the oxidation number of the hydrogen peroxide is going down as it gets turned into water, chemically turned into water. So let's see, a -1 going to -2, that's a reduction. And then in this one, if we have this hydrogen peroxide going to oxygen gas, the oxidation number is going up, and in this case we'll call that an oxidation. Now, the thing that is reduced, it is gaining electrons, it must be causing the oxidation of something else. So this hydrogen peroxide molecule is causing the oxidation of this hydrogen peroxide molecule. So this hydrogen peroxide molecule would be the oxidizing agent, whereas this hydrogen peroxide molecule, it's being oxidized, losing electrons, so it must be pumping electrons into something else. It's pumping them into here. So this hydrogen peroxide molecule that's undergoing oxidation, it's the reducing agent. So if the first problem is confusing a little bit, it's okay, that's a tough one. In that particular reaction, hydrogen peroxide is both oxidized and reduced, and it's also both the oxidizing agent and the reducing agent at the same time. I was a little mean to you on that one. Let's look at this particular reaction here. This is the reaction that's going to happen inside of your common battery, like a AA battery or a AAA battery. So in your AAA battery, you have some manganese 4 oxide. It's going to react with zinc metal and some water, and it forms zinc oxide. And this particular manganese species that I'm not going to name for you, we're not going to worry about that. But what's interesting about this particular redox reaction, it is a redox reaction, is that importantly for this quick demonstration I'm going to do for you, we see that zinc gets turned, we're going to figure out whether it's oxidized or reduced, into zinc oxide. And what's interesting about this is zinc oxide is bouncy. There are actually some patents out there for golf balls to include zinc oxide in the core, so that when they're struck, they'll go a little further, because they just bounce real easily off of the club when it's struck. So if that's the case, we're going from something that's not so bouncy like zinc to something that is bouncy. And so if the battery's fresh, there's going to be a lot of reactants present. There's going to be a lot of unbouncy material in it. And as the battery is used, it produces a lot of bouncy material. I think you might see where this is going. So there's really an easy test you can do to see if a battery is dead or if it's fresh. If it's fresh, when you hit the bottom of it hard on a flat surface, so I throw this down so the battery tries to strike like this, it doesn't bounce very well. If I do the same thing with a dead battery, all the zinc oxide in it causes it to bounce. So it's a really quick way to test to see if your battery is fresh or dead. This one, I'm going to throw in the trash. This one I'm going to keep. So let's look at this particular reaction and see if it's, well, it is a redox reaction, but let's see what's oxidized and what's reduced and so forth. So I'm going to start with something that's pretty easy. I've got zinc metal, which is an element. And you might remember those elements, that's rule number 2. We're going to assign the oxidation number of the atoms in an element an oxidation number of 0. And that should make sense. This thing has no charge, it's the only thing in there. So we better give it an oxidation number of 0 or rule number 1 is going to be violated. Let's look at what happens to this zinc over here. If we follow through the rules for this particular compound, you're going to end up assigning an oxidation number. I won't do that because that indicates charge. I'm so used to doing that. I'm going to give this an oxidation number of -2. And so since zinc oxide overall is neutral, it's easy to see. We better give that zinc a +2 charge. And so we see that zinc is oxidized. Oxidation number is going up. Zinc gets oxidized to zinc oxide in our battery. I'm going to tell you a little trick here. When you're looking at redox reactions, pay attention to the metals. It's usually the metals that change their oxidation numbers during oxidation and reduction reactions. So I'm going to focus in here on my manganese 4 oxide and this manganese compound, and let's see what's happening here with the manganese in terms of oxidation numbers. So with my manganese oxide, I'm going to need to assign an oxidation number to my manganese and my 2 oxygens. And when I'm done, this has no charge, so the charge on it had better, the sum of the oxidation numbers better equal 0. As I go through the rules, I see I don't need to follow rule 2 or 3, they don't even really apply. Rule 4 doesn't apply. I finally get down to the rule for oxygen, and I see that I'm going to assign a -2 for the oxidation numbers for both oxygens. Well, that tells me I better give the manganese a +4, and I'll do that. So my oxidation number for manganese in this particular compound is -4. It's probably going to be reduced, right? I mean, this is being oxidized, so this is probably the thing that's going to be reduced, because if an oxidation is happening somewhere, a reduction better be happening somewhere else. Let's look over here at this particular compound. I've got a manganese, and I've got 2 oxygens, and I've got a hydrogen. So I look through the rules. Rule 1 applies, of course. Better make sure the sum of those is 0. Rule 2 doesn't apply, it's not an element. Rule 3 doesn't apply, there's no monoatomic ion, it's a compound that we're dealing with. Rule 4, there's no fluorine. Rule 5, there's a hydrogen, so we're going to give that a +1. Rule 6 deals with oxygen, we better give those -2s. And now I'm stuck, and I need to assign this number. Let's see, -2 +1, overall that's -3. What do I need to add to that -3 to get to 0? A +3. So indeed, I see that manganese 4, we would say manganese 4 oxide, gets reduced into this goofy looking manganese compound. And we would also say that manganese 4 oxide, since it's reduced, is the oxidizing agent because it causes the oxidation of zinc. On the other hand, zinc, which is oxidized, the zinc is going to be the reducing agent because it causes the reduction of manganese 4 oxide in the battery.